Hey there, welcome back. Today we're going to talk about how to use double integrals to apply to a lot of different types of applications. So the main areas that we're going to focus on are going to be talking about area, volume, average value, probability functions, charge, mass, and the center of gravity of a region. Now, the basic ideas behind all of these is that when you're trying to find the a quantity, you can break it up into a lot of little pieces and sum them all together, and that will give you the answer. So for instance, if our quantity is area, we can simply find the integral of a whole bunch of little pieces of area, add them all up, that gives us the area. Similarly, when we want to find the volume, we add up a whole bunch of little pieces of volume. When we want to find a probability of a subregion, we're going to add up a whole bunch of little bits of probability. When we want to find the charge of some object, we're going to add up a whole bunch of little bits of charge. And when we have some mass, we're going to sum up a whole bunch of little bits of mass. And so all of these applications, they all might look a little different, but they're all this same idea. Finding one quantity, we're going to break up into a lot of little quantities. For this video, we're going to focus on the first three, and in future videos, we're going to talk about the other four. All right, so first area. So let's say we have a domain. So given a domain D, its area can be found by adding up little bits of area. So we might write area is equal to this double integral over our domain of 1 times dA. So we're in the situation where we have some region, and we'd like to figure out what the area of this domain is. Well, if we can set up an integral, a double integral, where we set it up maybe with respect to x and with respect to y, then when we take the double integral of this, maybe dx dy or dy dx, then we're going to get the area of this domain. In future videos, we're going to change what this little d area is. But in our cases, when we're thinking about a little bit of area and we've broken things up into rectangles, then d area is equal to a little dx times a little dy. But again, this is going to change, and this will be different when we're talking about triple integrals. All right, that's our basic idea about area. Now let's talk about volume. So, same idea. So given a domain D and a three-dimensional region that is defined as being between some upper function g of x and some lower function, g of xy, and some lower function f of xy on this domain. So what does that look like? We've got our domain down here, and maybe we've got some curves, and we've got our region here. We'd like to find what's the volume of this region. So we're defined over domain D. Then the volume of the region is V is equal to the integral of dV. And what we're saying is that for any little bit of area down here, the height of this region is what matters. So we'll write this as the integral of height times dA over our domain, which is the double integral over our domain of g of xy minus f of xy dA. And again, that's going to be either dx dy or dy dx, depending on the best way to represent our domain as a function of x and y. So that's the idea here of area and volume. And the last thing for this video is the idea of the average value of a function. Okay, so let's just get on the same page here about what the average value of a function means. So we have a function that is defined on a domain D. So it's some function that any point you plug in from D, you get a value out from the function. The average value of f is what happens when you smooth out this whole function, so it's all a complex function. If you wanted to like squish it down and pat it so that all of the high parts become low and all the low parts become high, so everything is completely flat. So the average value of f is asking to smooth out f so that it has the same height everywhere. So I'll show a picture of this in a second in Mathematica, but if you've got some function that's got some low parts and some high parts, well, what we're looking for is what's that average value for this function over this domain. Right? So we're flattening this down so that now there's no high parts, there's no low parts, it's all been evened out. So we have basically now a cylinder over whatever our domain was. So in other words, so mathematically, what are we doing? So in other words, we can calculate the volume under the surface and then divide by the area of our domain to find the average height. And so if we're writing that down, we would say the average value of f is going to be the integral over our domain of f dA divided by the area. Or we could write that as the integral of f dA divided by the integral of 1 dA. All right, so let's go over to Mathematica. I've set up a function here. This is the function 3 minus x quantity squared plus y plus sine of xy. You can see that this function, super wavy, not looking very pleasant. I don't think I'd want to integrate it either, but we could. So let's look at this and let's see what is the average value of this function. So the average value of this function is what happens when we take the volume under the surface and we flatten it out. So we can get Mathematica to integrate. This is a function of multiple variables, you can still use integrate or n-integrate to get the numerical approximation. And you can say, right now we're over the region that's this rectangle from 0 to 3 in x, 0 to 3 in y. And so we take the volume of that, we get that the volume is 43.2. Then we can find the area of the domain, which we know because it's a 3 by 3 square, so we should get the area is 3. So if we take the volume and we divide by the area, we get that the average height of this function over this domain is 4.8. So a nice thing we can do is we can flatten this out. So if we were to take all the excess height over here and and move it over to this side where there's not enough height, then everything would pack down to about this height, this green plane right here. That's the average value of the function. So what that's saying is that the amount of volume between the plane and above the curve is now the same as the volume above the plane and below the curve. Right, but Mathematica can also take integrals over non-rectangular regions. So let's say we had a region that was defined by this equation, where what we're saying is x minus 1 squared plus y minus 1 squared is less than or equal to 1. So a circle of radius 1 centered at 1, 1. So if we have that, this is the same function. It's wavy, but now the domain is a circular domain instead of a rectangular domain. Mathematica can still integrate over this region. You can use implicit region as the function and say, I want to integrate over this region of all points x, y that satisfy our equation. And we'll use the same n-integrate. And when we do that, we get the volume under the surface and above the xy plane. We can find the area. We know this is a circle of radius 1, so we get what we expect, that the area is pi. And the average value this time is going to be higher. It's 5.8. And we can see the same type of idea happening here where we have the area under our average value and above the surface is going to be the same volume as the volume below this surface and above the plane. All right, so that's a nice application. Come back for more. See you shortly.